In this lecture, we will analyze balanced passive mixer. We will try to find conversion gain and also try to find out the leakage, that means the feed through. So in the last class, we saw unbalanced mixer and it was based on switch. So this mixer that we are going to discuss today, balanced passive mixer and subsequent mixer, they will also be based on switches. So for the unbalanced case, there's only one single-ended so for unbalanced, we have single-ended nodes for LO, RF, and output, which is also IF. And we had implemented it also using a MOS, where it acted as a switch. And we found the conversion gain for this case. So here VRF is this one. So conversion gain was GC is equal to RL divided by RL plus RS into 1 by pi. And this is less than 1, that is why this is passive. And here there was issue that RF to IF feed through exist. And we did not include the gate to source or gate to drain capacitor. If you include, then there will be LO2 RF and LO2 IF feed through as well. So now what we are going to do, we are going to first talk about balance mixer, which has two different versions. First is single balanced mixer, and second is double balanced. So in the single balanced, this output port is going to be differential, and LO port is also going to be differential. However, the RF port continues to remain single-ended. And in the double balanced case, even the RF port also becomes differential. So now we will first take up this single balance case, that means this circuit, then try to find out the conversion gain and compare the conversion gain of this single balanced with this unbalanced mixer, and then try to see whether there is any advantage in terms of conversion gain also or not. In terms of feed through, we will see that this performs better. So in single balance case, what we do is we take two unbalanced mixers to create single balanced mixer. So we have this unbalanced mixer here. So this is one mixer. Then we take another mixer, unbalanced, like this, and interconnect their common input and then connect it to RF. And one of the LO is LO plus, the other is LO minus. So here you can see that LO and output, they are differential. However, the RF is single-ended. So for this circuit, our objective is to find out the conversion gain. And then find out the feed through. So because we will be carrying out feed through analysis, so we will be taking a little bit more realistic model for these MOS. So M1 and M2 both are going to act like switches. And it was pointed out that it is the parasitic capacitors which play important role in deciding the feed through. In fact, conversion gain also gets affected by their values. So we have to decide the model for switch. So ideally, we have been taking MOS like an ideal switch. So this is how we have been using up till now, but we are going to include the parasitics. So this is ideally, and now so the parasitic capacitors that we will include are going to be gate to source and gate to drain. So these two capacitors will be included. So in this case, now MOS so here we have gate, and here we have source, here we have drain. So between source and gate, we have CGS, and between gate and drain, we have CGD, and then there is a switch between here source and drain. So this is the switch between source and drain node. So now we will be substituting MOS by this model. And of course, this switch is going to get controlled by VLO, VLO plus or VLO minus, depending upon which MOS we are talking about. So now what we have to do is substitute the MOS by this model in this circuit and try to find out the output. So as we analyzed the previous case, unbalanced case, we uh, found out the output for one half of the LO, and then for the second half, and then combine them to get the final output. So, so steps that we will be following is first find VO for one half of LO, then find VO for the other half of LO, and then find the complete VO in terms of VRF. And then find out the amplitude of this output, and that divided with that of RF. So this will give the conversion gain. So here we see that LO is going to decide whether this switch is going to be closed or it is open. So we have to uh, assume a certain type of LO signal. So there are two ways in which LO signals can be assumed. It will be better to consider them as a square wave. So one is that we consider it between positive and negative values like this. So say this is VLO plus and sorry and VLO minus will be its complement. So this can be assumed between plus B and minus B. So this is VLO minus. So both are between plus B and minus B, and they are complementary. Or alternately, we can consider VLO of this form between 0 and say value B. Any of these two are okay. Yeah. So we see that during one part of LO, say for example, in this case, M1 is going to be on and M2 is going to be off. Same thing will happen here also. M1 is going to be on and M2 is going to be off. And for the second half, situation will reverse. For these two switches. So now we will take up the steps and try to find the output. So step 1. So we consider VLO plus to be high and VLO to be low, and this will imply M1 to be on, M2 to be off. So in this circuit, M1 is going to be closed switch, M2 is going to be off, and then we will have to include the gate to source, gate to drain capacitors here, and then try to find out what is this VO plus and VO minus because of this RF. So now let us substitute the MOS by switches, respective switches. So this is CGS, CGD, and here we will have LO plus, and the switch is closed now. The second MOS is off. So since all these capacitors gate to source for both the MOS, they are same. So what we are going to do is we will adopt a simplifying notation. We will simply say this is CS and this we will say CD, because we will be very often using these capacitors in the expressions. Okay. So this here VLO plus is present, here VLO minus is present, but we are interested in finding out this output due to this RF. So we will use the superposition and we will momentarily exclude these LO signals. So for that purpose, we will ground it. So So now you can see that we have RF, and this will give rise to, say, output VO1 plus and VO1 minus at the other terminal of the output. And we have to find out each of these two outputs. So now finding VO1 plus. So here we can see that now we have a network of R and C. Here we have RL, and on input side we have RS, and then CS and CD. So here we can see that this signal, RF signal, gets divided between this node and ground here via CS, then between this node and this ground, LO plus ground through CS and through CD and RL. So we see that at this a common source, which is the common to both M1 and M2, uh, there is a registered RS between S and RF, and there are four parallel elements: CS, PD, RL, and this CS. So we can see that for and this output that we are trying to find out, VO1 plus, is basically voltage at this source. So we can draw the equivalent circuit, and what we will get is something like this. One CS from this one, and then another CS from the M1, and then CD of M1, and then RL. So all these are in parallel and connected between source node. And then at the other end, we have RS and RF here. And the output that we are looking for is this output. So we can call this one as Z1. And now we can easily see that VO1 plus is Z1 divided by Z1 plus RS into VRF. And here Z1 is parallel combination of RL and XC. So what is this XC? XC is 1 by J omega 2CS plus CD. That means the combined effect of two CS capacitors and CD. So using Z1, we can now find out what is VO1 plus. Now we need to know what is this VO1 minus. So here we see that RF signal is actually isolated from this VO1 minus node. So for VO1 minus, we have to find out this voltage, which is across RL, and there is this capacitor between this node, which is say drain 2 and this ground. So for finding out VO minus, the circuit that we have is this one. So it is not connected with RF, because the RF signal comes from here, goes to ground like this via this CS. So that is why, therefore, VO1 minus is equal to 0. Now for the first half of LO, the net output is going to be VO1 plus minus VO1 minus. And this will turn out to be Z1 divided by Z1 plus RS into VRF. Okay. So in the second step, we will consider the second half of LO. So in this case, LO plus is going to be low, while VLO minus is going to be high. So here we will have M1 off, M2 on. So for this case, our circuit is going to look like this. So now this switch is open. While M2 is going to be closed. Okay. So this is the circuit for which we have to find out uh, output for the second half, and this output is going to be VO2 plus minus VO2 minus. So we have to find out each of these two outputs for this case. And we have removed VLO plus and VLO minus for finding out these two outputs. So now if we try to find out this VO2 plus, so again we have CD and RL separated from the RF. So in this case, circuit is RL, CD, CD is grounded, RL is also grounded, and this is VO2 plus. So therefore, VO2 plus is 0. Now for finding out VO2 minus, so here we see that between this RS and common source, we have RS, and then from this source, we have this CS to ground, this CD to ground, this RL to ground, and this CS to ground. So again, we have four elements in parallel. Two are CS, one is CD, and fourth is RL. So the circuit is now CS, CS, CD, RL. So this is Z1, same as what we found earlier. So VO2 minus is Z1 divided by Z1 plus RS into VRF. So therefore, VO2, which is VO2 plus minus VO2 minus, becomes minus Z1 divided by Z1 plus RS into VRF. So in the step 3, we can write a combined output or the complete output, and this is going to be equal to plus Z1 divided by Z1 plus RS into VRF for first half for second half. So we can take the common factor outside. So here we see that output is this factor Z1 plus Z1 divided by Z1 plus RS into VRF into a square wave. So this is a square wave, but now between +1 and -1 with frequency determined by LO. So we see that whatever may be the amplitude of the LO signal that we considered, the square wave here is always between +1 and -1. Only the frequency is determined by LO. And this VRF, let us say, is A cos omega RFT. Here. So now to find out the IF part, we need to multiply this with the uh, fundamental in the spectrum of the square wave. So therefore, VIF is Z1 divided by Z1 plus RS into A cos omega RF T into 4 by pi cos omega L T. So this will become 2 by pi A Z1 by Z1 plus RS into cos omega RF minus omega LO T plus cos so this is the amplitude of RF, or sorry, the IF or the output, and amplitude of RF or the input is A. So therefore conversion gain is 2 by pi Z1 divided by Z1 plus RS. So this is the conversion gain, and of course this is also going to be less than 1. So this implies this is going to be passive mixer. So this is single balance passive mixer. Now we can compare what will be the status of this single balanced passive mixer compared with the unbalanced case. So for that comparison here, since we have included all these gate to source, gate to drain capacitors here, these capacitors we have included, but when we derive the conversion gain for the unbalanced case, we did not include this. So we will have to remove these capacitors from here so that we can find out the conversion gain in their absence. So for CS CD is equal to 0, we see that Z1 becomes equal to RL. So then only thing that will survive here is this RL. So for this case, GC becomes 2 by pi RL divided by RL plus RS. And for unbalanced case, so we had found conversion gain to be 1 by pi RL divided by RL plus RS. So now we can compare the conversion gain of the two cases. So we find that for the unbalanced we have this value, and for single balanced we have this value. So we find that conversion gain for single balance is 2 times that of the conversion gain of unbalanced. So we now have advantage in terms of conversion gain also. That means output is going to be not so weak, not so small. And since now we have this output getting multiplied by a square wave, which is between +1 and -1, that means where which has no DC. So here you can see there is a no DC. So because there is a no DC, so on the output side, we do not see any RF. So RF does not get leaked to the output side. So first is RF to IF is absent because of no DC in the square wave. Which gets multiplied with RF. And if you recall the unbalanced case, so there was a DC because the square wave was between 0 and 1. So that is why that leakage was present there. Now let us try to find out LO to RF leakage, because now gate to source capacitor exists. So here now what we have to do, we have to treat LO as the source signal, and because of that we have to find out how much signal reaches at this source node. So we have to now include this LO plus and LO minus in the circuit, and then find out voltage here. So again, this has to be carried out in various steps. So first, consider LO plus to be high. So this will imply M1 to be on and M2 to be off. So now we are interested in finding out the contribution of these two to the RF port. So we have to find out say Vs plus. So we'll be calling this Vs plus voltage due to VLO plus at source. That means at RF port. Similarly, Vs minus voltage due to VLO minus. And we will be carrying out all these analysis by assuming only one of the LO to be present in the circuit. So we have considered the first half where LO plus is high. So in this case, M1 is closed, and we want to keep this, and because of this we want to know what is the voltage here. So we want to know what is this Vs. So we have removed VLO minus just to find out what is this Vs plus. And this is also during the first half, so we will be calling it as Vs1 plus. So now let us see that what is happening here. What we have is source is only voltage present is this one VLO plus. So now we have a parallel CES CD between LO plus and this source node, and at this source node and ground we have RS, we have this CS, and here we have RL. So there are three elements in parallel between source node and ground, and between LO and source, two elements, CS and CD. So equivalent circuit now is so here we have RL, or let us say RS. Here we have RL and ES. And this node is PS1 plus, right? RS, RL, ES, and then CS and CD. So this is purely reactive part, so we'll calling it as XC, and this we will be calling it Z2. So XC is 1 by J omega CS plus CD. Z2 is RS parallel RL parallel XCS, where XCS is 1 by J omega CS. So now we can write VS1 plus as Z2 divided by Z2 plus XC into VLO plus. So this is the contribution of LO plus to this node. Now we have to consider LO minus, and because of that, we have to find out the voltage at this node. So for this case also, the circuit remains same. But now we are going to remove LO plus, and VLO minus is going to be included now. So for this case, so we can see that between this source node and ground, we have RS, we have CS, CD, RL. However, between source and LO minus, we have only one element CS. So this case now the circuit becomes RS, CS, CD, RL. And on this side, we have only one element. So this is going to be Z3. So VS1 minus becomes Z3 divided by Z3 plus XCS into VLO minus. So this factor is different from this factor. So we can call this as alpha VLO plus, and this is certain factor beta VLO minus. Therefore, the total VS1 is going to VS1 plus VS1 minus, and this will turn out to be Z2 by Z2 plus XC VLO plus Z3 by Z3 plus XCS VLO minus. So we see that this is going to be in general non-zero. So there is a leakage of LO to RF even in the single balance case, because this port is single-ended. So maybe when we convert this to differential port, this might get eliminated. So this is the story uh, during the first half. So similarly, during the second half of hello, we will have a scenario exactly reverse of this. So from symmetry, you can guess that now we will have a voltage Vs2, which is going to be beta into VLO plus alpha into VLO minus. So again, non-zero voltage is present here. But what is happening here is you can see that LO to RF is present. Now this signal is going to get mixed with LO, because what happens in this circuit, in this mixer, is basically mixing up this RF signal, with LO. So if there is any signal present here at the common source of the two MOS, then that signal will also undergo mixing with LO. So here what will happen? LO will get, so this leaked LO will get mixed with LO. And we have seen that this will lead to DC at the RF port. So LO self mixing leads to DC. So this is undesired, and this one gets sorted out in double balanced mixer, where even the RF port is differential.